Hello everyone, welcome to Learning Math with Shobita. Today we discuss a question from Real Analysis which is asked in Kset 2023. The question is, let f from the open interval 0, 1 to r be a function defined by f of x equal to 0 for x irrational and it is 1 by q for x equal to p by q, p, q belongs to set of natural numbers and the GCD of p, q is equal to 1. Then f is continuous at option A, all irrational points on open interval 0, 1, or option B, all rational points on open interval 0, 1, option C, all points on open interval 0, 1, option D, all points of the form 1 by q for some q belonging to set of natural numbers. Let us see about the solution. Actually, the given function is Thome function. To check the continuity of a function at a given point, we can use one of the theorem. Let us recall that theorem. A function f from S to a set of real numbers is continuous at a point a belonging to S if and only if for every sequence xn in S which converges to A, the sequence f of xn converges to f of A. That is, a function is continuous at a point if for every sequence in that every sequence that converges to that point, the sequence f of xn must converge to f of A. Okay. Suppose that A equal to p by q is any rational number in open interval 0, 1. Then f of A will be equal to 1 by q. They have given in the definition f of A, this is 1 by q for rational numbers. Okay. Which is greater than 0. Since every neighborhood of a rational number contains infinitely many irrational numbers, therefore for each n belonging to n, we can find an irrational number an such that a minus 1 by n less than an less than a plus 1 by n, which implies the modulus of an minus a is less than 1 by n. This implies the sequence an converges to f a. But f of an equal to 0, since an is irrational and we have defined the function for irrational number, the function is 0. So f of an will be 0 for all n belongs to n. Therefore, limit n tending to infinity of f of n equal to 0, which is not equal to f of a. Thus, sequence f of an does not converges to f of a, which implies f is not continuous at a, which implies f is discontinuous at each rational point in 0, 1. Okay. Now let us see what happens if it is the number point is irrational. Next, suppose b is any irrational number, then f of b is 0 by the definition of function. Let epsilon greater than 0 be given. By Archimedean property of real numbers, we can choose a positive integer n such that 1 by n less than epsilon. Clearly, there can be only finite number of rational numbers p by q in open interval 0, 1, such that q less than 1. We can therefore find a delta greater than such that open interval b minus delta, b plus delta has no rational numbers with denominator less than n. That is, open interval b minus delta, b plus delta contains only those rational numbers p by q for which q less than greater than or equal to n. Thus, when x is irrational, modulus of x minus b is less than delta, which implies modulus of f of x minus f of b equal to 0, which is less than epsilon. And when x is rational, modulus of x minus b less than delta implies modulus of x minus f of b equal to modulus of f of x, which is less than, which is equal to 1 by q, which is less than epsilon. Combining, we have for any x real number x, whenever x minus b is less than delta, we got f of x minus f of b is less than epsilon. That is, f is continuous at b, which implies f is continuous at every irrational point. Thus, option A is correct. That is, f is continuous at every irrational points on 0, 1. Hence, option A is correct.